Okay, here's a quick draft of the Bloch sphere. Okay, here we go. So I'll start off with saying here's our general qubit, and the Bloch sphere is a way of helping us visualize the state of the qubit. And the point is that these coefficients, the general qubit is a linear combination of the two basis states with complex coefficients. So at first glance, you would think that you need 4 separate parameters to specify the state of a qubit, because after all, complex numbers each have a real and imaginary part. But that's not really the answer for 2 reasons. One is that there's a constraint that the state be normalized. So we require that if you square and then sum the magnitudes of these complex quantities, you always get 1. So that's one constraint. And then the other constraint is that the global phase doesn't matter. So we can explain that with the following. So global phase doesn't matter. So what do I mean by that? Well, you can express any complex number in sort of polar form of its magnitude times e to the I, and then I'll call the phase angle here phi sub alpha. And similarly, the complex number beta you can write as the magnitude of beta times e to the I phi sub beta. And so we can always write, we can always choose to write an arbitrary, our states phi in the following form. I'm going to factor out this e to the I alpha phi like that, and I can write my qubit in the following way. Like so. And, you know, the claim is that 2 wave functions are essentially indistinguishable if you have 2 wave functions and they just differ in the following way. You can't distinguish psi prime from psi if psi prime is just some phase of some factor, some complex number of magnitude 1 times psi. So this global phase doesn't matter. So the upshot is you can ignore this e to the I phi, and you could always write, without any loss of generality, the wave function as some real number times 1 plus you can always write a wave function this way, where the coefficient in front of the 0 is a real number, and what really matters in specifying the state of the qubit are essentially the ratio of the magnitudes of beta and alpha and the relative phase. So I need to figure out a way to say that more clearly, but that's the point. So the bottom line you want to emphasize is it really doesn't take 4 parameters to specify the state of the qubit. It really takes 2. What's going to end up mattering is the relative phase between the 2 parts, which is going to be captured by this term here, and then the relative magnitudes of beta and alpha. So we want to capture that some way. And here's how we're going to do it. We're going to choose to write psi in the following form. There are going to be two parameters. One of them is going to be this angle theta, and we're going to write psi as cosine of that angle theta divided by 2, and then the next term is this relative phase, e to the I phi times sine theta over 2 times 1. Okay, so this is in this form in which we have a real quantity here, and then this relative phase factor here times another real quantity. And notice, I mean, it's easy to see that by doing it this way, we ensure that we satisfy the first constraint, that the square root, the magnitudes, the sum of the magnitudes of the two coefficients out in front sums to 1, because the magnitude, this just says, it's pretty clear that the magnitude of the first coefficient is cosine squared theta, and then the magnitude of the second coefficient, well, e to the I phi has a magnitude of 1, so the magnitude of the second coefficient is just sine squared theta over 2. And that's clearly going to be equal to 1 for any choice of the angle theta. Okay, so given that, we can specify the state of the qubit just by specifying these two angles, theta and phi. That's the big idea. And then we want a way of visualizing it, and that's where the Bloch sphere comes in. And so we can just view the state of the qubit in sort of spherical coordinates. We're going to imagine a spherical surface here, and just like a globe, you can specify points on the globe by specifying a latitude and longitude. It's almost exactly like that, except it's actually the co-latitude here. So if this is the North Pole here, then the angle theta is measured with respect to that North Pole, and so that's the co-latitude, and then this azimuthal angle phi here is measured with respect to the x-axis. So each unique qubit is going to occupy a different point on the Bloch sphere, and then we'll be able to visualize not only the state of a qubit, but when we make a unitary transformation on the qubit, we'll be able to visualize that as a change in the position of the qubit as to what location it occupies on the Bloch sphere. Okay, so now in this one, we'll look at the location of particular qubits and where they are located on the Bloch sphere. So let's start off with we're representing our general qubit in this form, cosine theta over 2 times the zero basis state plus e to the I phi sine theta over 2 times the 1 state. So for the zero basis state, that implies that cosine theta over 2 has got to equal 1, and e to the I phi sine theta over 2 has got to equal 0. So clearly theta must, for this state, be equal to 0 degrees or radians. And phi is actually indeterminate, because once theta equals 0 makes cosine theta over 2 1, and then that makes sine theta over 2 0, and we don't really know what phi is for this state, but it doesn't matter because we're at the North Pole, right? So the longitude of a point is not really specified when you're at the North Pole. So this is the 0 state, right at the North Pole here. And then similarly, the 1 state, 1 basis state, that must mean that cosine theta over 2 has got to equal 0, and e to the I phi sine theta over 2 has got to equal 1. So that implies that theta has got to equal pi radians. I guess I should have put this in radians. Because if theta is equal to pi, then sine pi over 2 is 1. And again, phi is unspecified. So the 1 state is at the south pole, as you can see in this drawing here. So theta has gone all the way over to pi. So the 1 state is at the is diametrically opposed to the 0 state in this Bloch sphere visualization. Then another familiar state would be the plus 45 degrees state, or let's just call it the plus state, which recall is defined as 1 over the square root of 2 times the 0 state plus the 1 state. So that must mean that cosine, in this state, cosine theta over 2 has got to equal 1 over the square root of 2. And that's also got to equal sine theta over 2. And the relative phase here is 0. So e to the I phi has got to equal 1. So that implies that theta has got to equal pi over 2. And in order for e to the I phi to equal 1, it's got to be true that phi is equal to 0 radians. So that means that this state, the plus state, is located right at this point on the Bloch sphere, because it has a co-latitude theta of 90 degrees. We're right on the equator, and the phase angle is 0 radians, and that's measured with respect to this x-axis here. So the plus state is right where I've shown it. And then similarly, let's talk about the minus state. The minus state is 1 over the square root of 2 times the 0 basis state minus the 1 basis state. So that means that cosine theta over 2 is still got to be 1 over the square root of 2. So that must mean that theta is still equal to pi over 2. But now e to the I phi times sine theta over 2 has got to equal minus 1 over the square root of 2. So that means that e to the I phi has got to equal minus 1. So if e to the I phi is equal to minus 1, that must mean that phi for the state is equal to pi, because e to the I pi is equal to negative 1. Okay, so the minus state here is located on the equator, 180 degrees diametrically opposed from the plus state. And you'll notice here that again, the minus state is diametrically opposed from the plus state. The 0 state and the 1 state are diametrically opposed, or antipodes of one another. That's not an accident. It's a direct consequence of the fact that when two states, it turns out, and I'll prove this in a second, that if two states, any arbitrary states, are orthogonal to one another, they will occupy diametrically opposed points on the Bloch sphere. So let's prove that. So here's how I would do the proof. Let psi be any state on the Bloch sphere as before. So psi is characterized by its angles theta and phi. And so let's suppose another state psi prime is the antipode, is, and what I mean by that, of psi. What I mean by that, I mean it's diametrically opposed. So if psi is here, then you just go straight across through the diameter to get to psi prime. Well, so it's pretty easy to see, as I've tried to illustrate in this drawing, that if psi prime is diametrically opposed to psi, its colatitude is just pi minus theta. That's pretty obvious since the total angle here is pi. And then what's harder to see from the drawing, but is pretty easy to see if you think about it, is that the phi, the longitude associated with psi prime, is going to be whatever phi is plus pi radians. So if you go, you're standing in Boston and you want to go to a point on the globe diametrically opposed from us, you're going to end up a little bit in southwestern Australia. The longitude there is going to be 180 degrees greater than whatever the longitude is in Boston. So having said that, we can write psi prime is going to be the cosine of pi minus theta over 2 times 0 plus, oops, erase, plus e to the I pi plus phi times sine of pi minus theta over 2 times 1. Okay, and the cosine of pi minus theta over 2 is, it's easy to see that that's equal to the sine of theta over 2. That's just a trig identity. And then I can write e to the I pi plus phi. I can write that as e to the I pi times e to the I phi. And then the sine of pi over minus theta over 2 is just the cosine of theta over 2 times 1. Okay, and then this e to the I pi is minus 1. Okay, so psi prime then is sine theta over 2 times 0 minus e to the I phi cos theta over 2 times the 1 state. So now it's easy to see that psi prime is orthogonal to psi, because if I calculate the inner product of psi prime and psi, I can write that as sine theta over 2. Remember the rules. When you move something from a ket to a bra, this e to the I phi here, it's a complex quantity, it becomes an e to the minus I phi times cos theta over 2. This is the way we take an inner product. And then the psi term here is a cos theta over 2 e to the plus I phi times sine theta over 2. Okay, so the way to calculate the inner product is to multiply this row vector by this column vector, and what do we get? It's the first times the first, so we get sine theta over 2 times cosine theta over 2, and then plus the second term times the second term. So we're multiplying minus e to the minus I phi times plus e to the I phi, minus e to the minus I phi cosine theta over 2 times e to the I phi sine theta over 2, e to the minus I phi times e to the plus I phi just gives 1, and we're left with a negative sign here, and then it's cos theta over 2 times sine theta over 2. So that is equal to 0. So any two states that are diametrically opposed to one another are orthogonal to one another. And then the last thing I would point out is that if you go to the Quark tool at alglassert.com here that we've been looking at, you can play around with understanding sort of what different transformations do in terms of where they end up on the Bloch sphere. So if you drag different gates into the different lines here, so if you start at the 0 state, which is up here, and you operate with the Hadamard gate, you transform the 0 state into the what we call the plus state, and that's what's being indicated here. If you start at the 0 state and then you knot it, you end up going to the minus state. So anyway, it's interesting to play around with the various combinations of gates here and sort of using the Bloch sphere representation to get a visualization of what these different transformations do in terms of changing the position on the Bloch sphere. So that's it, and that's the early draft of my What's the Big Idea on the Bloch sphere that I'm going to share with Cora and Jiatong, but hopefully I'll polish it more, and it will become a useful tool that we'll use in Physics 323 this semester. That's all for now. Bye-bye.